Okay. So, well, it's my great pleasure to introduce Émeric Baradat. He's now in the Université de Lyon, member of the CNRS, and is going to talk about a joint work with Hugo Lavenant. And it's about entropic minimization with respect to branching Brownian motion. So to my opinion, this is Schrödinger problem. But instead of having a diffusion process, then you have a branching process and the mass will not be conserved. So Émeric, you can go on.
Thank you, Christian. Thank you very much for the organization and for the invitation. I'm sorry that I'm not with you in Lisbon. I hope it will be easier for me next time. So yes, I will talk about entropic minimization with respect to branching Brownian motion. And as Christian said, it's really about replacing the Brownian motion from the standard Schrödinger problem by the branching Brownian motion. And the overall goal of this project is to see that doing so, we recover an optimal transport problem, just as in the standard case, but this optimal transport will be unbalanced in the sense that the mass is allowed to vary during the evolution. So it's been a long time that I'm working almost exclusively on this project, so I already gave several talks, and some of you have already seen some of them, so I decided to do a talk that's a bit different. Let's say usually I do some advertising talk showing the asymptotics, the applications. Today I want rather have a mathematical talk, so I will try to enter the detail, and in particular what I will present is how to build a correspondence between competitors. So from a law with finite entropy with respect to the branching Brownian motion, how do I build a competitor for the optimal transport problem and vice versa? Yeah, and the proof will go through actually characterizing all the laws that have finite entropy with respect to the branching Brownian motion, and we will see that these are just branching Brownian motions, but with a modified branching mechanism and where the particle have an additional drift. So let's go, but before I need to introduce what's the branching Brownian motion. So the branching Brownian motion, basically what it does is at the initial time you have a certain amount of particles, and each of them are independent and follow Brownian trajectories. And at a certain rate, they die and give birth to a certain amount of new particles. So sometimes they die and there is no other particle. Sometimes they have more than two, so it's something very general, and you have several particles like this. And what you're interested in is the measure valued process corresponding to the empirical measure of the particle alive at time t. So the process is the sum of delta xit, where I is a label for the particles alive at time t. Okay, and xi is the corresponding position. So this process is characterized by several parameters. So first by a diffusivity coefficient, which is a positive number for the Brownian trajectories. Then the rate at which a particle dies and gives rise to k particles. So I call it qk, which is a non-negative number. So rate at which k particles appear. And I take always k different from 1, because if a particle dies and is replaced by exactly one particle, it's exactly the same as if nothing had happened. And all this qk, I store it in a big Q. Okay, Q is the collection of qk, and actually I see it as a non-negative measure on the set of integers. Okay, I just do some assumption on this qk. I assume that the rq, which is the sum over qk times k minus 1. So this is the growing rate of the number of particles, because at rate qk, you create k minus 1 particle, because remember this one corresponds to the fact that one particle dies at the branching event. And this number, I assume that it's always finite. And for the remaining part of the presentation, I need also to define the lambda q, which is the sum of qk, and it is the rate at which there are branching events. Okay, so I don't have enough space for the rest. So the last parameter is a R0, and R0 will be the initial law of the branching Brownian motion. So it's a probability law on the set that I call M delta of TD, which is just the set of empirical laws. Okay. So R0 is a way to select at random an initial configuration for the particles. And once you have these three coefficients, the nu, the q, and the R0, what you have is that, so given nu, q, R0, there exists a unique R. I write it like this, that it follows the law of the branching Brownian motion of this corresponding to these parameters. And it belongs to the set of probability laws on a certain set omega, and omega is the set of Cadillac curves with values in the set of measures. Okay, now the process is with values in the set of empirical laws of sum of Dirac. And on this, so this is the so-called canonical space. And on this canonical space, I define the canonical process, like the evaluation map. So say it's the process whose law is R. So now to define the branching, what I will call the branching Schrödinger problem, what I need to tell you is if I have a law on omega, how do I define the density corresponding to this? So if P is a law on omega, so in the following P will be like the competitors for the branching Schrödinger problem. And if I take T between 0 and 1, so the so-called intensity of P at time T is the measure. So this time is just a non-negative measure on the torus. Yeah, I didn't tell, but I will always work on the torus. And which is defined by rho pt is simply the expectation with respect to P of MT. So P is a law for this process MT. And what you do to have this intensity is that for all Borelian sets, you count the number of particles that are in A at time T, and you take the expectation of this number with respect to P. So this is rho pt of A. And the remark is that if P equals R, actually this rho R solves a certain parabolic equation, and this parabolic equation is dt rho R equals nu divided by 2 Laplacian rho R. This is because the particles follow Brownian trajectory. And now there is a growing term, and this growing term is exactly the RQ that I defined in the previous slide. So this is the way it appears. So now I'm able to define the branching Schrödinger problem. And so the data for the branching Schrödinger problem, it's just as in the Schrödinger problem, two non-negative measures. So an initial measure and a final measure in the set of non-negative measures. And what I look for is the optimal value of the following problem. So the optimal value, I write it like this. And this is the infimum value of the relative entropy of P with respect to R under the constraint that the intensity at time 0 of P is rho 0 and same at time 1. And just as in the classical Schrödinger problem, actually, in order to have something that's of order 1 when nu is small, you need to put a scaling factor like this. Okay, so now I have one optimization program, the branching Schrödinger problem, and I want to see that it's equivalent to a certain optimal transport problem. So this is what I will define now. And this optimal transport problem, the parameters of this problem are still a diffusivity coefficient, but also a convex function that has all the good properties. And which goes from R to possibly infinite values. And it corresponds to the cost of creating mass in the problem. Okay, and so now the regularized, so this optimal transport problem, I call it regularized and balanced optimal transport problem. And it's defined by, so if I take rho 0, rho 1, some non-negative measure, I want to find the following optimal value. So this is the infimum of an action on a certain triplet. So in optimal transport, we would only have rho and v, the density and velocity. Here, there is also a growing rate. So this action of this triplet is the same thing as in optimal transport, plus a certain cost for creating mass, time rho dt. And the constraint is that rho at time 0 is rho 0, rho at time 1 is rho 1, and a certain continuity equation, which is dt rho plus div rho v, equals, so rho r, this corresponds to the fact that now we are unbalanced, and there is a nu divided by 2 Laplacian rho, which corresponds to the fact that the problem is regularized. Okay, and so now when I, oh, what's up? Oh, we have a problem here. Ah. Okay. So now when I will talk about triplets rho v r, it will always be understood that they solve the continuity equation. Okay, so now I have two problems and I want to show that, that these problems are equivalent. But in order to do it, I need to tell you how to select the psi. Because in the branching Schrödinger problem, you have two parameters which are nu and q, whereas in the regularized and balanced optimal transport problem, you have two parameters which are nu and psi. So how to choose psi so that the two problem corresponds. And so actually, what we do is that given nu q as before, we define psi through its Legendre transform, psi star by, so psi star of z is nu times the sum over k of qk exponential k minus 1 z divided by nu minus 1. So this is what you have. So for instance, if nu equals 1 and q0, q2 equals 1/2 and qk equals 0 otherwise, you find psi star of z is the hyperbolic cosine of z minus 1. So this is something that has that is exponential on both sides of z. And so what it tells you is that actually what I find in this kind of problem is psi of r to be of order r log r, when r goes to plus or minus infinity. So this is, let's say, below the standard quadratic case. That's the most studied unbalanced optimal transport problem. Okay, now I want to show you why this is this psi that pops up in the computations. And for this, I need to introduce a last notation. So if I take two non-negative measures on the set of integers, I will call with a little h, and I will still call it the relative entropy. So it's like the relative entropy, but adapted to the fact that q and q tilde are not probability measures anymore. So the formula is something like this. So I put qk's everywhere, and then I put the tildes at the right place. So like this. And the fact is that this psi is the infimal value of the relative entropy of q tilde with respect to q under the constraint that the growing rate corresponding to q tilde is r. So h of q tilde q, you have to see it as the entropic cost of changing the branching mechanism in the branching Brownian motion, and the cost of going to the growing rate r is the infimum of all these possible entropic costs, knowing the growing rate. This is why this is this psi that appears. So now I'm able to state the main theorem. I just need to give a few assumptions. I won't develop so much because actually we won't go sufficiently deep into the proof to see really the assumptions, but still I don't want to state some false results. So I take nu q r0 as before, r the corresponding branching Brownian motion. and psi defined by the previous slide. And what we assume, so the main technical assumption is that we have some exponential moments. So this is what I will not develop so much, but it writes like this. So this exponential moment is finite, and same for Q. So yeah, I want you to trust me that it's not very restrictive. Then we need something else. It's that R0 is not the direct mass at 0. So we want to have an actual branching Brownian motion. We want that at least sometimes there are a few particles. If there is always 0 particle, it's not very interesting, but the result would be false. And the last assumption, actually, this is not a true assumption. This is just for simplicity. So we can relax this assumption, but I would need to introduce some additional tools that I don't want to talk about. So what I will do is that I will set ρ0 to be the initial intensity of R. So all the optimal transport problem, I will see them as transporting ρ0 to ρ1, and what will vary is ρ1, not ρ0. I keep ρ0 fixed. Else I would need to introduce another optimization program at the initial time, but I don't want to talk about it. So the theorem tells that both problems are equivalent. So somehow what we would like to state is that if I look at the optimal value in the optimal transport problem, this has something to do with the optimal value in the branching Schrödinger problem. So the best thing would be that these two numbers are equal. But actually, it's not true. But what is true is that if I look at this functional, then this is the LSC relaxation, the lower semi-continuous relaxation. Of the second functional. Okay, so actually this problem is the good problem, the good well-posed variational problems, that's lower semi-continuous, blah, blah, blah. Whereas this one is a bit more, it's slightly ill-posed, and that's why you don't have an equality, but just a lower semi-continuous envelope. And this is for the weak star topology of measures. And moreover, so the most interesting part, according to me, is that there is a relevant correspondence between competitors. And what do I mean when I tell this? Well, I mean that first, if I take P, a competitor for the branching Schrödinger problem, so if I take P with finite entropy with respect to R, then there is a triplet ρ_r solution of the continuity equation such that the action of ρ_r is lower than the corresponding relative entropy. And why do I say that this correspondence is relevant? It's because if I look at the ρ_t, it's actually the intensity of P at time t. Okay, so this is the first correspondence, and the second correspondence goes in the other way. It's that for all ρ_r, solution of the continuity equation with A of ρ_r finite, then there is P with mu h of P with respect to R is lower than the action of ρ_r. And once again, the fact that this correspondence is good means that the intensity of P at time t is ρ_t. So if these two correspondences were true, then actually the result, there would not be any lower semi-continuous relaxation. The fact that it's a lower semi-continuous relaxation, it's because here I need to have an additional assumption, and this additional assumption is the fact that I have to assume V and psi of R to be bounded. Oops. So the remark is that the second point, the correspondence between competitors, implies the first one, because if you look at A, actually the optimal cost in the optimal transport problem is below the optimal costs in the branching Schrödinger problem. Because as soon as you have a competitor for this problem, you can find, thanks to this, a competitor for the optimal transport problem with the same marginals. So it's a competitor with the same ρ0 and ρ1. So you have this inequality. And second, because of B, so what you have is that for all ρ1, there exists a sequence weakly converging to ρ1, and such that the optimal value in the branching Schrödinger problem is below the optimal value in the optimal transport problem. Why so? Well, because if you take a competitor for the optimal transport problem between ρ0 and ρ1 without an n, you can always regularize it in such a way that V and psi of r become bounded. In that case, you can take ρ1 n to be the final value of this regularized curve. And for this regularized curve, you have a correspondence. And the last remark that I will do is that, of course, because you have this inequality and this inequality, in the case when you have the reverse inequalities, actually the inequalities are equalities. Okay, so now the remaining part of my talk will be about proving this correspondence, these points A and B. And in order to do so, so once again, it will go through characterizing all the laws that are finite entropy with respect to the branching Brownian motion. And for this, I need a few tools of stochastic calculus. And in particular, I need to introduce some processes under the law of the branching Brownian motion. And the first process that I need to introduce is a generalized stochastic integral, and it's defined as such. So if V, if it's a smooth vector field, we define, so the generalized stochastic integral, I will write it like this: the integral of V at time t is simply the sum on all the particles of the following stochastic integral, the classical one. So okay, so what I do is that if I have a time t, I look at all the branches of the branching Brownian motion and I integrate the vector field along each branch and I sum up everything. And here, sorry, Bi and Di are the moments of birth and death of particle I. So when you do so, what you get, this I of V is a continuous martingale under R, and its quadratic variation is, so I will write it with square bracket because the angled brackets, I use it for something else, is this. So integral between 0 and t of, so V of S is a vector field, there is a new, and I integrate it against a certain measure, and this measure is exactly ms ds. So for each particle, if there is a particle at position x at time s, I sum V of S and x squared. I do the sum for all the particles. Okay, now the question is which vector field I can integrate in that way, because for the moment I took some deterministic smooth vector field, actually, we don't need this at all. We can always take random vector fields. When you do some stochastic integral of something, the integrand can always be random. And I don't need it to be smooth. I don't even need it to be defined everywhere. I want just that if at time t I have several positions like this, I want the vector field to be well defined on each of these positions. And by the classical theory of stochastic integrals, actually, these vector fields, they have to depend on the past of the process only. So this vector field could depend, for instance, on the past of this particle. This is allowed to depend on all this, but you don't have the right to depend on the future. Okay, so so the 2 points that I just said is that V can be random, but predictable. And it means that the value of V of t can depend on the past only. So I'm a bit sloppy here, but I don't want to enter too much into the measurability details. And the other thing is the well definition of V. V needs to be defined so almost surely, I want it to be defined for almost every t, and not everywhere, but just empty almost everywhere. Okay, and if these 2 points are satisfied, we say that V is a predictable vector field. So it's a predictable field. And I put the vector into parentheses because, of course, you can have predictable fields of other objects. Okay, so this is the first process that I wanted to introduce, the generalized stochastic integral. If V is a predictable vector field, actually, this proposition is still true. And now I need to introduce another process, which will be a jump process. So let's say that in the Brownian case, all the martingales are continuous martingale and they correspond to stochastic integrals. In the branching Brownian case, you can also have jumps at the moment of the branching event. So that's why I defined the following process. So given a predictable scalar field, so this time this is a scalar field, and k different from 1, I define jk of t is, so it's the process which adds a of t and x each time there is a jump with k particle. Okay, so you can write it as an uncountable sum where only a finite number of terms will be non-zero. So you can define it like this. So a big something times a of s and x. And this big something is that branching event with k particle at sx. So when you do so, you get like a pure jump process, and the goal when you do discontinuous stochastic calculus is always to find some compensators for this kind of objects. So I just give an illustration of this notion. So how do you find martingales out of such processes? And here is a kind of proposition that you can get. So if A is bounded, then actually your jka of t, if you remove it a certain finite variation process, which is simply, so once again, A of s, this is just a scalar field, and you can integrate it against the measure ms ds, then you get a martingale. And you could do better than bounded, but I don't want to enter the details. So now I can sketch the proof of the theorem, and I will first prove the B part of the theorem, which is the so how do you get a competitor for the branching Schrödinger problem out of a competitor of the optimal transport problem? So what I will show is that I can construct a lot of branching Brownian motions where I add drifts and where I change the branching mechanism of these branching Brownian motions. So if I take V tilde and Q tilde, some predictable fields, so now they depend on Tx and the randomness. If V tilde and H of the relative entropy of Q tilde respect to Q are bounded, so this is where the boundedness appears, then you can define a law P by prescribing its Radon-Nikodym derivative with respect to R. So this is the kind of Gersonov formula for the branching Brownian motion. So the formula is like this. You take 1 over nu, the generalized stochastic integral of time 1, plus the sum over k of jk, sorry, you need to, this is a V tilde. So this is what you need to take. And then you need to remove a finite variation process in such a way that actually this is the value at time 1 of an exponential Martingale. And what you need to remove is V tilde of t squared divided by 2 nu plus the lambda q minus lambda q tilde of t that you integrate against mt dt. So when you define it like this, so it's a generalization of how you change from the law of a Brownian motion to a law of a Brownian motion plus a drift. But here we also change the branching mechanism. So this is the law of a branching Brownian motion with drifts V tilde and branching mechanism Q tilde. And moreover, once you have this formula, you can actually have an estimate on the entropy of P with respect to R, even an equality. The entropy of P with respect to R, you can compute it, and it's the expectation with respect to P of something that looks like the classical case. Okay, you have the V squared, but this time you also have the entropic cost of changing the branching mechanism. All these are fields, so you can integrate them against a measure, and the measure is mt and dt. So this is where you see that the entropic cost of changing the branching mechanism is exactly the relative entropy of Q tilde with respect to Q. So how do I use this result to find a competitor of the branching Schrödinger problem out of a competitor of the optimal transport problem? So if I take rho v.r, a competitor for the optimal transport problem with the boundedness assumptions that I asked. Then we can build the P built in the previous slide with a particular choice of V tilde and Q tilde. And this particular choice is, so V tilde of T and X, instead of being random, you take the determinist one, V of T and X. And for Q tilde of T and X, actually you take the optimizer of the relative entropy with respect to Q under constraints. That the growing rate corresponding to Q tilde Tx is simply R of Tx. Okay, and when you do so, if you look at this formula, which is the formula that I gave in the previous slide, you find that the relative entropy of P respect to R is the expectation of, so now the V tilde is replaced by a V. And this new H is actually replaced by psi of R, because you know that the optimal value of this under this constraint is psi of R. So this is what you get. And now what you integrate here is deterministic. So you can take everything outside and you end up with integrating this against the expectation under P of MT, but this is nothing but rho P. So what you find is and so the last thing that we need to check, so actually this is A of rho VR, because as we can check that rho P equals rho. And so to check this, it's just because there are two solutions of the same linear parabolic equations. Okay, so we have the first correspondence, and now actually we will see the second one. And for the second one, actually what we need to prove is that any, so I remind you that now I want to take a competitor for the branching Schrödinger problem, and I want to show that I can take out of it a competitor for the optimal transport problem. And so what I need to prove first is that if I take a competitor for the branching Schrödinger problem, it's actually a branching Brownian motion with a drift and a changed branching mechanism. So the first thing is to say that out of a P that has finite entropy with respect to R, there is V tilde and Q tilde, some predictable fields such that first, P is the law of a BBM with drifts V tilde and branching mechanism Q tilde. And second, with a certain estimate, so we can control with the entropy the functional that I introduced before, which is EP plus H of Q tilde T with respect to Q and T. So I will tell in a second how we find V tilde and Q tilde, but first I want to show you, once you have this V tilde and Q tilde, how do you build a competitor for the optimal transport problem? So the problem is that here, this V tilde and Q tilde, they are random, and you need to build some deterministic triplet for the continuity equation. You know? So you do this like this. So for the rho, you just take the rho PT, okay, no problem here. For the V of T, what you do is that, so it's as in classical optimal transport, the additive quantity is not the velocity, it's actually the momentum. So what you take is the random momentum, which is V tilde times MT. Then you take the expectation with respect to P of this value. You can see it as the total momentum. Yeah. So this is a vector valued measure. And now you take the Radon-Nikodym derivative of this measure with respect to the density. And then you find the vector field, and this is the VT that you wanted. And for the RT, you do something similar. I will take more space. For the RT, what you take is that you take the random growing rate. You take the corresponding momentum, so you multiply it by MT. You take the expectation with respect to P. So this is the total momentum. This is a measure. And now you take the Radon-Nikodym derivative with respect to the density. And if you do so, actually, you can see that by Jensen, So the quantity that's here is actually bigger than the same quantity with v instead of v tilde and psi of r instead of this quantity. And just as before, this is exactly the same as a of rho v r. So you have one. So now what I want to show you is out of a P, how do you get this V tilde and Q tilde? And I think it's quite of a beautiful argument that's actually a generalization of an argument by I mean, it's a direct adaptation of an argument by Christian in a paper in 2012, and it relies on functional analysis. And the idea is to use a general inequality which is just the convex inequality for the relative entropy. So if I take Z, a random variable, the idea is that I can always estimate the expectation of Z under P. So you see that you can see it as a duality bracket between P and Z, and you can always estimate it by this nonlinear convex function of P plus its Legendre transform applied at Z. And the Legendre transform of this convex function is actually the log of the expectation with respect to R of the exponential of Z. So this is the inequality. And the idea is to use this inequality with particular smart choices of Z. So the second thing is to apply this to Z being the generalized stochastic integral of some W at time 1 minus something that you need to remove in such a way that the exponential of Z is the value at time 1 of an exponential martingale, so that actually its expectation will be 1 and this term would be cancelled. So you can do the computation and see that what you need to remove is this. And so now if you write this, what you get is that EP of this stochastic integral, so W here is just some typical predictable vector field. Then this part, I will put it on the right-hand side. So this is lower than the entropy of P with respect to R, plus the thing that corresponds to the right-hand side, because here I told you that this is 0. And so what corresponds to the right-hand side is this. And now if you look a bit this formula in the eyes, what you realize is that the first thing is the linear form on W. The second thing is the constant in the sense that it doesn't depend on W. And the last thing is actually an L2 norm of W. In a space that I won't describe exactly, but you see you have W squared that you integrate against first MTs and DTs and P. So this is just an L2 norm. So you can use the Riesz representation theorem and get a predictable vector field such that for all W, the linear form is nothing but the scalar product against V tilde. And the scalar product is something like this. Well, it's exactly this. And now you have the V tilde, and actually you need to check that it's indeed the drift of the particles, but it's possible using a martingale approach. And you know, in Riesz, so you have an estimation like this. You use Riesz actually. This V tilde comes with an estimate on its L2 norm, and actually the estimate on the L2 norm will be exactly something like this. You know that the L2 norm of V tilde will be smaller than something that depends on the relative entropy. And now, to close my talk, I need to tell you how you find the QK. And actually, the idea is almost the same. So it's to apply the general inequality with Z being this time the jump process at time 1 of some predictable scalar field, minus what you need to remove. This time you can do the computation and see that it's qk, so something like this, if I'm not mistaken. And what you get is that, so this linear form, it's a linear form on A, is smaller than the entropy plus qk times the expectation with respect to P of this. So now you don't have an LP norm anymore, but still you have a superlinear control on A. So this linear form is controlled by a certain quantity, a nonlinear quantity of A, a superlinear quantity of A. And actually there are some versions of the Riesz representation theorem in the space, for instance, in the space of function whose exponential is integrable. So it's called Orlid space. And there is q tilde k such that for all A, this linear form is the scalar product against q tilde k. And once again, you need to check that actually this q tilde k is indeed the branching rate of P, but you can do it using martingale arguments. And now, so in the Riesz representation theorem, what you get is an estimate on the L2 norm of V. Here, what you get is an estimate on the Legendre transform of this function estimated at Q. And actually, this is something that like Q log Q, Q tilde log Q tilde. So actually, this is why you find this entropy. It's because the Legendre transform of the exponential is the Q log Q, let's say. Okay, so I will stop here. I hope I convinced you that it's quite of a nice subject with something from stochastic calculus, some calculus of variations, some functional analysis. So I really enjoyed working on this. And I hope the preprint is ready very soon. Everything is written and now we are just proofreading it. So thank you very much.
Thank you, Enric. Are there any questions from the remote people from internet? This one? No? Okay. In the audience? Yes? All right. So, Gabriel.
So could you explain what the connections with Wasserstein-Fischer-Rao type problems and this type of thing? And is it obvious?
So I didn't understand correctly, but what you asked me is if there is like a small noise limit converging to Fischer-Rao or something like this?
To unbalanced optimal transport Wasserstein-Fischer-Rao, is it what you said?
So actually, so once again, here we don't have the quadratic cost. We have something that's exponential. We can still perform a small noise limit, letting nu tend to 0. And we also need to rescale the Q. And in that case, we cannot find the quadratic cost, but we can find unbalanced optimal partial transport. So the absolute value, where the psi is the absolute value. This we can show a gamma limit convergence towards the optimal partial transport.
And is there extension to other type of the transport, or it's out of it?
I didn't understand. Sorry, I don't hear very well.
Sorry, I'm saying, is this possible? I mean, at least maybe formally to extend this construction to other types of unbalanced optimal transport?
We tried several things. So actually, we have some formal computations that allow us to replace the branching Brownian motion with any super process. So let's say measure valued process where the the mass is allowed to vary. And so we tried several things. And for instance, we tried the super Brownian motion. And in this case, we find the quadratic costs, but we don't have the right to move. So it's an asymptotics where the cost to, we find the quadratic cost, but there is no transport anymore. So, I mean, if there are some other super process, I mean, we could try things. We have some formal computations, but so far we didn't find anything as interesting as the branching Brownian motion, where you have both the transport and the creation of mass.
Okay, thank you very much.
Question from Dimitri to everyone. What happens if the transport part vanishes and only reaction is left?
And only
reaction is left.
Sorry, I don't understand.
So the question, it's written on the chat. You can see it.
Okay.
What happens if the transport part disappears, but you only keep the reaction part? Probably it means the birth and death process.
So you want to do the entropic minimization with respect to just a branching process without anything. Then you can do exactly the same, and you find just some. So, I mean, something that's more related to total variation distances, something like this. I mean, you can always write your transport problem, which is not really transport anymore because there is no transport anymore, but still you can get exactly the same as in here, but where you remove the V. So you remove the V here and in the continuity equation.
Are there, this was a question by Dimitri. Okay. Leonard has a question. Hi, Mike. Can you make the problem somehow time symmetric? Because both the branching Brownian motion and your continuity equation are kind of forward in time. So it seems kind of artificial that you go forward in time, but backward, or mix both, as Jean-Claude likes to do.
That's actually a question that interests me a lot, but I don't have an answer so far. What's clear is that the standard trick in the classical Schrödinger problems that you can either put the Laplacian in the continuity equation or put the Fisher information. So in the classical case, it's equivalent. In our case, it's not. So it's
right, because BBL is not reversible, right?
No, here it's not reversible. So, but of course, if we could replace the branching Brownian motion by any process that's reversible, then we would find something reversible. And actually, I was very interested into the talk of Max yesterday, because this is really some kind of process that we could try. So it would be some balanced. So it would be some balanced thing, but still with some things that's probably different from just the standard optimal transport problem.
Well, I think for that you would need to allow coalescence, but for a discrete number of particles, that's kind of, it's never going to happen. It's like probability zero. So you need a continuum of particles. Or am I wrong, Max? No. No.
No.
No. I mean, in dimensions higher than 2, Brownian particles will never collide, right? If you have
exactly.
Of them,
and that's why the talk of yesterday was about dimension 1, as far as I understood. But still, it would be something. I mean,
okay.
I would like to do the computations, actually. I was quite excited.
Thank you.
So it's Christian again. So this was part of my question anyway. And the second part of the question by Leo is, well, if you can build this reversible branching and killing process, you think it would be achievable to have, as Giovanni did with the usual Schrödinger problem, to get some Newton equation or to have a natural geometry for the space of positive measure in the way we have the Otto-Wasserstein geometry for the probability. So You
I
think
mean,
it's achievable?
it would be wonderful.
Yes,
Of
okay.
course.
This is a program.
Yeah. So far, we are just, we
Yes,
didn't have the time to consider this, but of course, it would be a natural question now.
it would be very beautiful. Yes.
Yeah.
Okay, so, well, no more question. Thank you very much, Emeric, for this beautiful talk. Thanks a
Thank
lot.
you.